So this is, as Professor Sharma has already shown, these are these very boring two semiconductors with huge band gaps, and the merger of them gives rise to this metallic conduction. So that's the first emergence, that two semiconductors, as we often say, that the semiconductors are boring, particularly these ones, whereas the correlated oxides are extremely intelligent but wayward. Controlling parameter control is extremely difficult. So then poor materials. So the question was the marriage of these two, what will happen? And this is this age-old question, Bernard Shaw and Isidore Duncan. Then there is always a 50-50 chance that you get the opposite of what you wanted. So Bernard Shaw's beauty and Isidore Duncan's brawn. So, but fortunately here the opposite happened, and this is that famous the resistivity going down and then becoming metallic. Okay, so I'll just keep this because I come from IIT. We are bound to show an application. Anushree missed it. Be very careful. So we have to show an application slide nowadays. So this is the one, and this is how you get these systems. These systems are almost always backgated. So I do not know why you don't front gate it. There must be a reason you don't front gate. Okay, so this is the this is Manhart's one of his series of papers. See, what was interesting is that you need 4 layers of LaAlO3 to produce the metallicity. So this 4 is like a magic number, and I haven't seen any explanation of this 4 from any real theoretical hard calculations. But this is true, it is 4. So this is another experiment, and okay, so let me skip. This is something that Professor Sharma has already shown, that you have these two kinds of planes, BO2 and AO, and they have, depending on what your A and B are, they have different charges. They can be neutral or they can be polar. So in the system that we are talking about has this so-called polar LaAlO3, and then you can do this very simple calculation, and it all is everything that comes is because of this constant of proportionality, constant of integration, because that adds up at every layer, and then it immediately runs away as the number of layers go up. So you can you heard that this can be controlled, and remember that the fields here are exceedingly high simply because the denominator is angstrom, nearly 0.4 nanometer. So and so the control is done by this +5 and -5 charges, which produce a capacitor, and this then again it's a very simple back of the envelope calculation that tells you that then the potential is no longer a runaway variable. Okay, so let me just skip. So the other interesting thing here is that this is a point that he was also mentioning, that the more oxygen the better the sample is, the worse the conductivity in this metallic region. So you need a bit of disorder to make it perfectly a very good conductor. So it's just opposite to what normally happens in bulk. There is a paper from, again, almost every paper you can say Manhart's paper here, but it's almost true. I have actually checked. So Triscone and Manhart are almost authors in almost all papers that come out. Then this doesn't come out, right? Exactly. So absolutely. So this paper showed that you actually don't need oxygen vacancies. This, I mean, since I'm not an experimentalist, I can always show the data and then don't have to defend them. So this shows that they claim that this ratio is very critical, and if you have a perfectly stoichiometric compound, then of course you don't have this metallic conduction. So you need to, so PLD samples like MBE samples which are here are doing bad. They are not, they don't produce this metallic conduction unless you deliberately disordered them. Whereas the PLD samples which are here does this job. of producing this metallic layer. So this is one of his 154 samples, out of which he chose 54, and these experiments were done. So it's actually a very thorough set of data. Okay, so the second emergence was the superconductivity at the interface, and this was really striking because you can even have a superconductor to insulator transition without going through the metal as a function of both gate voltage and magnetic field. It critically depends, the TC critically depends on the number of layers. 8 seems to be a very good number for highest TC. This is the gate voltage tuned transport, superconductor to insulator transition. It happens at around this Holy resistivity, this E of Feregal number. Okay, so this is something that Kalu was asking, Professor Maiti was asking, and then this is the superconducting dome, and this is as a function of gate voltage. So I have not seen this mean field behavior drawn by anybody. Everybody draws this diagram, and so as a function of gate voltage, this is how it behaves, and you can actually take sort of believe, if you believe that there is a quantum critical point here, then you can draw a line, and that line fits beautifully with the z nu bar equal to 2/3 exponent, and that is actually the exponent that you get from z is the dynamical critical exponent. So that sort of indicates it's a BKT kind of transition. So that's one paper that claims it's a BKT, and this is what the difference between a pure SRTiO3 becoming superconductor and this sample. So I am not getting into this. Okay, so this is the other criterion that you can look at to see whether this is a BKT transition or not, and this exponent is being half is another indication that this is a BKT transition. And now, of course, Avik Bid has this long paper, noise spectrum, I mean the noise of resistivity, spectrum of that, and they find a very strong non-Gaussian component, which we actually simulated, and we reproduced his data. Okay, so the superconducting gap, the DIDV, behaves like this, and then of course you see this is the BCS value, and then if you plot this gap from here, it sort of behaves like a BCS in that sense. If you think of BCS as a mean field, then the exponent here around is half. So, but then this gap is not really related to TC. That is the other interesting thing. So if you do a 2 delta by KB TC, you will not get 3.5 here. If you do 2 delta by KB T gap, then you will get 3.4. So that's an interesting observation, that you put TC, it will be much higher. This will be around 20 or so. So the people compare with high TC superconductor, there is this T star, and here is this so-called T gap. So features of superconductivity are these, that you have it's believed to be LO phonon mediated, carrier density is low, plus 13, sorry. TC shows BKT behavior, this is 3.4. It coexists with ferromagnetic puddles of large moments, so this I will come to. And enhancement of superconductivity by magnetic field, this is another interesting observation. And there is of course this observation from Bangalore, the ISC, that there is a hidden region of superconductivity which you don't normally see, but see only in transient magnetic field. So if you put transient magnetic field, the TC goes up. So it just appears, superconducting phase appears above the dome. So this is this was emergence, magnetism, coexistence of superconductivity and magnetism. And as I heard from him, that there are regions, there are systems, samples where you don't see it, there are many samples where you see it. So the samples that are reported here had both superconductivity and ferromagnetic, and this is the landscape. There are regions of ferromagnetism and superconductivity, both are distributed in sort of patchy way. The other interesting thing is that the moments are highly planar. I mean, there is absolutely almost no z component to this moment around the 001 direction. There are many measurements now on this, and there is just one controversy, which is that the Stork magnetometry finds half the magnetic moment than the squid. So that is more or less now resolved experimentally. Okay, so this the other interesting thing is that you normally don't touch your squid on the surface, but if you do, then you can actually carry these magnetic patches along with this squid tip. So it's very soft. This actually indicates this is from this NUS group, and they sort of claim that there is a strong indication that there is a phase separation. These large hysteresis loops are sort of indicative of that. Okay, so let me just the brief time I have, tell you what we have been doing. So these are the issues at a glance. There is a quasi 2D electron gas at the surface, which we just heard in the morning is a highly unresolved problem. Where does it come from? There is a superconductivity below 300 millikelvin. There is ferromagnetic order even up to 200 Kelvin from two non-magnetic oxides. There is a coexistence of superconductivity and magnetism. There is electric field induced superconductor to insulator transition. Critical LO, this is 4, that magic number 4. Then of course there is something that we proposed, is there a possible region of Majorana excitations. Then the nature of superconductivity, then of course this hidden superconductivity. In this Bangalore group is our collaborator. I mean, we are their collaborator rather. They found it, and there is this question of vacancy ordering, which I think Professor Das has asked in the morning, and there is this resistive noise. This is also a collaboration, and signature of Lifshitz transition. This we proposed, and it's now seen. And sign change in magnetoresistance has just come up last year, and we are working on it. So these colored things which are not black are the things that we worked on. Okay, so this is the simplest electronic structure one can think of. This is proposed by Lee, and so there's a D1 Ti3 plus. So there's a D1 electron, and that has to go to this DXY, which is the only one which is sort of free in 2 dimensions. So this is the one. This band, DXY band, is stabilized by just simply Heisenberg uncertainty because it has no Z extent. These other ones are 1 dimension. So that's it. Okay, so let me skip it. So the model that even Patrick Lee also wrote down is the same as that we are using, and this is the standard, except that we have this Rajba spin orbit coupling, strong spin orbit coupling, and we have BCS pairing term. Okay, so this is the bands. These are the bands, and this is it's a very simple Hamiltonian. Since there is a strong spin orbit coupling, spin is not a good quantum number, but you can describe everything in terms of helicity. So that's what one does. The interesting thing is that now you can see that at gamma point, the 2 Fermi surfaces, Fermi levels are at different points, and so if you want to pair an electron from here to here, which we normally do, then you must give a finite center of momentum. There is no other way you can pair them up, and that's what one does. So this is a pairing of electrons at finite momentum and spin mixing. Now, since the superconductivity and the magnetism coexist in this system, ferromagnetism in particular, the first proposal of course came from Patrick Lee that this is the discovery of an FFLO state. Okay, so we will actually look at it. That also has a finite momentum pairing. Okay, so let's just remember that this system is highly disordered, so you just cannot do a homogeneous calculation, and you have to sort of solve it on a real lattice, and we did it using this Bogoliubov of Digen's standard theory, and we put in a disorder, and so we actually worked through these self-consistent solutions, and the highest we could go was to 32 by 32. Now, if you look at this is superconductivity, magnetism is suppressed here. As disorder increases, the regions of superconductivity become patchy. This is magnetism. This shows that again this becomes patchy as disorder increases, and then you put them together, and then what we saw is that interestingly that where there is magnetism there is no superconductivity, and they sort of beautifully intermix amongst themselves and avoid each other, so that there is a clear phase separation. Now since we are working in a non-ergodic system, disordered, we had to talk in terms of probabilities. So you just this is the homogeneous result, and then as disorder increases the probability shifts towards 0. Okay. So let me just keep all this. This is something here, of course we had to take a Fourier transform, so we need to restore the ergodicity. So we did it for 10,000 different situations, and then average them, and then you can do a Fourier transform. So this is interesting that what you can see is that the rho sub s superfluid density is actually fairly robust with respect to disorder, and that is what you see in these systems, because the superconductivity survives even in the most disordered system. Okay, so let me skip this. The other issue was that the magnetism was increasing as I told you with the temperature, and what we find is that it's actually not that magnetism is increasing, it's the superconductivity is going down and the regions available for magnetism is growing. So it's just simple number that the magnetic moment that you find is just larger. Okay, so let me skip this. We also looked at oxygen vacancy clustering, and what we did is that we deliberately put in the vacancy in this calculation, and then after every iteration, every time we solve the problem, we use that free energy to calculate just fed it into Monte Carlo. So this was done in a Monte Carlo calculation, and we actually found that indeed there is a region where oxygen vacancies are clustering. Let me just skip this. Then we there is a we could see that you can also see that these spins being mixed, you are bound to have a POF pairing in this system, and because there is a spin or strong spin orbit coupling, the time reversal symmetry is already broken, and you have and there is magnetic field, so it's already broken. So you are going to have a complex order parameter. That's possibility exists. So we looked at this idea. There is a paper by Reed and Green who suggested that if you have a topological superconductor coexisting with magnetism, then it is possible to have a Majorana bound state. So we actually tried to find out what is the region where I can have topological superconductor in this system. And I just skip this because this is Kitaev's famous 1D demonstration that you can actually pair up electrons in this fashion, and then two Majorana fermions at the two ends become free. So they have to be far separated and they will be free. So you can actually get Majorana fermions at the two ends, two edges. So then what we did is that to get this P plus this topological superconductor, we realized that you cannot get them if your pairing happens from two bands. So we put a magnetic field which is along the z direction, so that this other band goes up, and we can pin our chemical potential right in the middle. And once this happens, then as you see the two Fermi shifts are gone, only one Fermi surface exists, and now you have the pairing here, and this pairing can be, so let's see what happens. If you have this situation where both the Fermi surfaces exist, then you have both P plus minus IP pairing. So the sign averages out and you do not have a topological superconductor. Once you are in this region, crosses this value, then you can have topological superconductor. So this is the region where we should look for Majorana fermion. But it is also important that the chemical potential has to go to 0. So to produce such a situation, what we did is that we put in a vortex, magnetic vortex inside this superconductor. So this vortex core has chemical potential 0. So that is where we should look for the Majorana fermion. So once we put in the vortex and we did this problem again, in that region where you have only P plus IP, this is the geometry we suggested. So this is B region, is the region where you have P plus IP. So this is where we are, and then let me just skip. Then we were looking for zero energy excitations. Since this is a P plus IP superconductor, there is a finite gap, so it's not gapless anywhere. So as you can see that, these are 32 by 32 into 2 states, so some of which are being shown, and as you can see these red lines, these are magnetic, they are proportional to H sub Z, so that is, these are not Majorana, but then suddenly you enter, this is the region where we are supposed to enter the B region of the phase diagram, this region, and that is where suddenly we picked up this zero energy excitation, and it is just completely invariant under magnetic field, alpha, the spin orbit coupling and everything. So we had a strong suspicion that this is the Majorana fermion, Majorana bound state. So with Hz also, as you can see, it's just nothing is happening here. So then we, with some trepidation, we actually put it up on the archive, and then within about 6 hours we got a mail from Manhart saying that he has also seen it, and he sent us his data, and these are his data, and he asked us to compare with his data. But comparing theory with experiment is non-trivial, because the numbers are just, ours are just completely, everything is 1, t equal to 1, alpha equal to something, all in that unit. So we converted, and we could see that indeed there is some match, 60 to 70% match with his numbers, and he also saw it in one of his samples. It's called T64. That sample showed this kind of a zero bias anomaly, and that's exactly what we see. And interestingly, we actually then checked with gate voltage and magnetic field, and that matches where it should appear. So we sent back our report to him, but he is of course careful. So he has now published the data with my student. So okay, so this is the other problem that we did, which is the question of the anti-side disorder in this system. And since there are two different kinds of oxides, then you can have the possibility of this anti-side disorder, and that's what Andy Millis and company actually looked at. Let me just go through it quickly, not giving everything. So in the sense I don't have time. And what we did is that Andy Millis and company only looked at the anti-side disorder. What we did is that we actually included oxygen vacancies. For them it was no vacancy system, it's perfectly pure, which we believed was not possible. There has to be oxygen vacancies, and then we put in oxygen vacancies, and we found the trouble there is that with oxygen vacancies, this unit cell is huge. There are 21 different samples that they studied, which we also studied. Each of them has 4 magnetic states, and then there are 2 unit cells possible, and 2 different locations of the disorder, and 4 different places for anti-side disorder. So 84 into 4 into 2 into 2. These many calculations you had to do. These many DFT calculations. So it took about 1.5 years. But what we finally resolved is that Andy Millis's results are probably not kosher, and the anti-side disorder, actually they showed that anti-side disorder is favored. We find that it completely depends on where the oxygen vacancies are and how they are. So then this is the other problem that we did, that we actually noticed that these 3 bands coming too close together. My chairman is getting jittery, so let me just finish fast. These bands come closer here, and we predicted that there should be a Lifshitz transition at this point. If you can change your gate voltage to tune your Fermi level here, and this is the calculation. Here we took care of all 6 bands and all possible combinations of superconducting order parameter. So we predicted, and then we did a Monte Carlo to calculate, because this disordered system, it's the phase coherence that matters, not the amplitude. So we did such a calculation, and we found that indeed the superconductivity is this kind of island-like, patchy, and we found the LDOS and so on and so forth. But we also found that there is a region where the transport will show up the Lifshitz transition. We just mentioned it. But then there is a paper that came in Nature Communication, which we did not notice at that time, and they have now refined the data where they actually showed that this blue is the expected behavior of n and this red is the behavior they see, and they have mentioned that this is a region of Lifshitz transition. So let me just skip all this. Then we actually turned back and we looked at the Lifshitz transition, and we did find the Lifshitz transition, and this is how so then we actually showed that to look for Lifshitz transition, it is better to look into this. You see, the data shows there is a huge region for this Lifshitz transition, say about 100 volt. You cannot delineate in this region. Any value can be n sub c. Whereas we actually showed that if you look at Seebeck coefficient, thermopower, then it is much better because there is a huge cusp at the Lifshitz transition point, and we went ahead and we showed that you can actually have 3 different Lifshitz transitions depending on what field you are using. So instead of 1, you can actually have 3 different Lifshitz transitions. I think I don't have time beyond this, and so this is basically the conclusion. This is a very hard problem, and I like this cartoon because you should never give up. Thank you so much.